Hi. So this time I start a new topic. It is the Laplace equation. So this is the following equation. X equals x1, xn in Rn. So we consider it in the n-dimensional space, starting from n, even from n equal 1. The unknown function u of x equals u of x1 xn, and the equation is the following: d2u dx1 square plus d2u dx2 square plus and so on, plus d2u dxn square equals 0. It is Laplace equation. It is because of its importance and its ubiquity, we denote the left-hand side by delta u. Delta u equals d2u dx1 square plus and so on, plus d2u dxn square. And so our equation is delta u equals 0. It is capital Greek delta, and this operator delta is also called Laplacian. Just it is a noun, Laplacian. Laplacian operator, or Laplacian of u is 0. So this equation was in the center of the theory of partial differential equations and of mathematical physics in general for more than 2 centuries, and still now it is under study. So it is a very rich equation. I would say, unlike the wave equation, this equation is much more interesting. Now, for example, in case n equal 2, we have equation d2u dx1 square plus d2u dx2 square equals 0. So you see it looks similar to the string equation, but instead of minus here we have plus, and this plus changes the picture very much. So we will not see any similarity with the string equation in the theory which is going on. I am going to tell you. Now let me discuss briefly what sort of problem can result in the Laplace equation. So consider the following example. It is the problem of filtration of incompressible fluid in a porous medium. Now, here we have some terms which are not so terrible. So what we are talking about? What is porous medium? Porous medium is for example, a sand. Sand is a great example of porous medium. It has grains of quartz, solid grains of quartz, and the gaps between them, the spaces between these grains where the fluid is able to move. Yes? And practically we have the following. We have somewhere subterranean layer of sand. For example, and this sand is saturated with water, so it is all the spaces between the grains in sand are filled by water. Now we drilled a well from the surface to this sand and start to pump out water. So water is moving up stream, up this to the surface, and so it is somehow going toward the well to fill the space here. So we have the flow of the water in this in the sand to the well, and then it is moving, it is pumped up to the surface. So how to describe this situation mathematically? We have here, first of all, some function p of x. It is the pressure. So pressure is some function of x. Then next we have, because the pressure is a variable, here we have depression. So here, because of the work of this pump, the pressure is lower than aside. We have the pressure gradient, pressure difference, which pushes the water toward the well. Yes, so we have another field that is velocity field, velocity of water. So P is water pressure, P of x, V of x, water velocity. No, in practice, if you are not very close to the well, the velocity is small, but nonetheless it is enough to fill, fill the space which is was previously occupied by this water. Now some volume of water is pumped up, so the water from the side comes and replaces it. So this velocity is maybe small, but not zero. Now, what are the equations describing this situation? First equation is called Darcy Law. This equation says that the velocity of the fluid is directed in the direction opposite to gradient of the pressure, and it is proportional with some coefficient k. So V, let me put this arrow to show that V is a vector. V equals minus k gradient of P. Let me remind you what is gradient. If you have a vector, if you have a function, say p of x, equal p of say x1, x2, x3. No, we are in three-dimensional space. Then gradient p of x is a vector dp dx1, dp dx2, dp dx3. Yes. So velocity is directed along the vector gradient p, but in the opposite direction, from higher pressure to lower pressure. Now, I say that the fluid is incompressible. No, water is practically incompressible. We require very high pressure to considerably decrease the volume of water. So what does it mean? This means that divergence V is 0. So what is divergence V? So V of x equals, say, V1 of x, V2 of x, V3 of x. So this is components of vector V at the point x. And divergence V of x equals dV1 dx1 plus dV2 dx2 plus dV3 dx3. This is called divergence. And if the velocity field is incompressible, if the fluid is incompressible, then divergence is 0. Yes? So if you substitute here, so divergence V equals divergence of V is minus k gradient P. Equals minus k divergence of gradient P. Now it is, so we have to substitute now gradient P dp dx1, so minus k divergence of dp dx1, dp dx2, dp dx3. Now we have to substitute it in this formula of divergence. Yes? And we get minus k times d dx1 dp dx1 d2p dx1 square plus d2p dx2 square plus d2p dx3 square. And this should be 0. But this is a constant, and what is in the bracket is the Laplacian. So this means that Laplacian P equals 0. So the pressure inside the porous medium when we have the flow of incompressible fluid is satisfies the Laplacian equation. Yes, we will use this, I would say, hydrodynamical model because it makes some statements either obvious or easy to see or easy to prove. So it is very useful model. No other similar situation is electric current. So what does it mean? We have some medium, also homogeneous medium. One moment. With conductivity sigma. Conductivity sigma. Now in this medium we have electric potential phi of x, electric potential. And we have the current I of x, electric current. So if we are in inside this thick piece of say some material, conductive material. No, it can be metal, it can be some semiconductor, something like this. It has some conductivity, and the electric current, which is a vector field, where the charge is flowing. And here we have also two relations. First, the Ohm's law, which says that I of x equals minus sigma gradient phi of x. Yes, so the charge flows in the direction of decrease of the potential. And second, that if we want the picture to be time independent, stationary in time, this means that the charge does not accumulate anywhere, so the charge density should be constant, and this means that divergence I of x equals 0. And we have similarly divergence minus sigma gradient phi equal 0. Minus sigma divergence of gradient phi equals 0. And divergence of gradient of any function, it can be potential, it can be pressure, it can be some maybe function with some different physical meaning. It is the same as Laplacian. So minus sigma Laplacian phi is 0. So Laplacian phi is 0. So here in this problem of electric current distribution, or what is the same electric potential distribution, we have the same equation. And we can always have the same equation in the study of, say, the gravitational potential, yes, or in the study of heat flow in the some material, yes. So the temperature in the homogeneous medium, also if it is stationary in time, satisfies the same equation. Yes, and so this equation appears in, I would say, innumerable amount of number of situations. And therefore this equation has been in the center of all mathematical physics for starting from early 19th century till today. I would say that it is the most, I would say, prominent partial differential equation. So now mostly we will study not applications, but the equation itself and some properties of its solution, and in some simple cases how to solve it. So let me now consider some properties, some examples, but before all examples, I have to formulate and prove the really basic property of solutions of this equation. First of all, if the function, say phi or p or any other, satisfies this equation, if Laplacian f is 0, then f of x is called harmonic function. Harmonic function. So I will call harmonic function. It is also a very popular term in all of mathematics, even beyond partial differential equations. Now, the question is the following, I would say, what I'm talking about. Consider, say, equations in the plane. So we have the plane xy, and the equations delta u equals du d2u dx square plus d2u dy square is 0. And now let us use different coordinate system. Coordinate system which is turned relative to this. Say we have, this is psi, and this is eta. So instead of xy axis, we consider psi eta axis, which are also perpendicular, but form with the x-axis and y-axis some angle. Let us call it phi. So let us turn the coordinate system. And we can also find function, find the following thing: d2u d psi square plus d2u d eta square. And suppose that this function is harmonic in the sense that this sum of second derivatives is 0. So my question, which I am asking now, is this function harmonic also in the coordinate psi eta? Yes? So is it equal to 0? I put here question mark. And the theorem, if theorem d2u dx square plus d2u dy square equals d2u d psi square plus d2u d eta square. So this means that not only harmonic function in the xy coordinates will remain harmonic function in xi eta coordinates, but even the value of the Laplacian in this coordinate xy is at the same point is the value of Laplacian in psi eta. Yes, so you can take say harmonic function and turn it, it remains harmonic. Yeah, it is far from obvious because if you say consider instead of this operator d2x dx u dx square plus d2u dy square minus instead of plus, it immediately breaks down. So it is the property exactly of this equation, of this operator. Now, this is the theorem, and it is really basic theorem because in the follows, what follows, we will from time to time really change coordinates or turn the function. So we need this theorem. So I have to prove it. Now, the proof is the following. We honestly compute the function, compute this Laplacian in the old and in the new coordinate. We'll see that results coincide. So let us do it. So what are the formulas when you go from xy to xi eta, or from xi eta to xy? So we write xi equals x cosine phi minus y sine phi. Eta equals x sine phi plus y cosine phi. So these are formula transformation from xy to xi eta. Now let us find how transforms the derivatives. Here we use the chain rule for functions of two variables, and I would say that we will use different facts about these functions of two variables, like integral formulas, this operator, divergence, gradient, maybe curl, and so on. So I advise you to repeat these things before going forth. If you don't understand, maybe better to go a little back and look in the calculus too about what does it all mean and how to work with it. Now I will work as if you know it all. So du dx equals du dxi dx plus du d eta dx. equals dx dx from this. It is cosine phi. Cosine phi du dxi. D eta dx, it is sine phi. Plus sine phi du d eta. Now du dy. Du dy equals du dxi dy plus du d eta dy equals dx dy is minus sine phi. Du dxi and d eta dy, it is cosine phi plus cosine phi du d eta. Yeah, so we found the first derivatives. Now let us find the second derivatives. Second derivatives. d2 u dx square. Oh, I'm sorry, it is wet. d2u dx square equals d dx du dx. Yeah, equals d dx. What is du dx? It is cosine phi du dxi plus sine phi du d eta. Now it is a function, so we apply the same formula. It is cosine phi. Now we have to differentiate this with respect to xi. Cosine phi d2u dxi square plus sine phi d2u d eta dxi. Yeah. Plus sine phi plus sine phi, and here we have d eta cosine phi d2u dxi d eta plus sine phi d2u d eta square equals, no, let me make some simplification, cosine square phi d2u d psi square plus cosine phi sine phi d to u, and here sine phi cosine phi, and these two derivatives are the same, plus cosine phi sine phi d to u d psi d eta, and remains sine square phi second derivative eta plus 1 moment 2, because we have it twice, sine phi d to u d eta square. So we found this, and d to u dy square, so we have to write minus sine phi from here, d psi of minus sine phi du dxi plus cosine phi du d eta plus cosine phi d eta of the same minus sine phi du dxi plus cosine phi du d eta. So what is this? Minus sine theta sine square phi d to u d psi square minus sine phi times cosine phi, sine phi cosine phi d to u d psi d eta plus no, here cosine minus sine minus cosine phi sine phi d to u d eta dxi, and remains plus cosine square phi d to u d eta square, which is equal sine square phi d to u d psi square minus 2 sine phi cosine phi d to u d psi d eta plus cosine square phi d to u d eta square. Okay, and now let us add, so to find the Laplacian. D to u dx square plus d to u dy square equals, the first is cosine square phi, and from here plus sine square phi d to u d psi square plus here we have 2 cosine phi sine phi, and here we have minus 2 cosine phi sine phi d2u d psi d eta plus sine square of course phi plus cosine square phi d2u d eta square. Now this cancels. Cosine square plus sine square is 1. It is equal simply d2u dc square plus d2u d eta square. It is in old coordinates xy. It is in new coordinates xi eta, and you see that they are equal after this transformation of coordinates. So the theorem is proved. When I prove a theorem and finish the proof, I write this symbol OK, so everything is OK. Yes. And so, why it is important? Why it is important? It is important because this means that harmonic functions do not depend on coordinate systems. The fact of harmonicity function it does not depend on coordinates. Yes, we can take these coordinates or take these coordinates, and the function which was harmonic remains harmonic. Now I proved this in 2 dimensions, and the theorem if Xi equals some A I J X J and A I J is an orthogonal matrix. Orthogonal matrix, it is a matrix of rotation, yes, which does not change the length of vectors. It's orthogonal matrix then some d2u dxi square I from 1 to n equals some d2u dxi j square, j from 1 to n. So the same result in any dimension, that if you change from one coordinate system to other, so that the coordinates are just rotate, yes, so the coordinate change is rotation. So either we rotate the coordinate basic vectors, or we rotate the space with the function in it. But anyway, in the corresponding points, the Laplacian is the same. Is it computed in the new or in the old coordinates? This is really important basic things. No, I don't prove this theorem. You can think yourself how to prove. In fact, it is reduced to the previous theorem. You simply say in 3 dimensions you can obtain any rotation by composition of 2 rotations in 2 coordinate planes. So you can think about this yourself. Yes. Okay, and now I can go and give you several examples of harmonic function. For now we had no examples at all. Now example 1, it is u of x equals some say ai xi linear function. Of course, this function is harmonic because all its second derivatives are 0. So let me call it example 0. Example 1. U, say, of xy equals x squared minus y squared. You can see that it is harmonic. Delta u equals second derivative is 2, second derivative minus 2 is 0. Next, u of xy equals xy. Yes? No, here if you find so u xx equals u yy equals 0. But in fact it is one and the same example, because if you take this quadratic function x squared minus y squared and then you write x xi equals x plus y divided by square root of 2, eta equals x minus y divided by square root of 2. Yes, so it is rotation through 45 degrees. Yes, so it is xy and this is xi and this is eta. Yes, and after that the function x squared minus y squared is converted into function xi times eta. Yeah, so in fact it is one and the same example. Next example is more interesting. No, in general. Example 3. U of x equals some aij xi xj, ij from 1 to n. So here x in point in Rn. Then Laplacian of u, if you compute, if I equal to different from j, then second derivative is 0 with respect to xi or to xj or to any other x. But if I equal to j, then second derivative is 2. So this means that only diagonal terms where I equal j count here. So it is 2 sum a I equals 2 trace a. Yes, A is this matrix with elements Aij. Yes, no, sometimes it's also useful. Now let us consider a more interesting geometrical example. Example 4. Consider in the xy plane the function, it is a point xy, and the function is this angle phi. Let me denote it theta. Theta is polar angle. It is defined everywhere but at the origin, and so how to find its Laplacian, this function. So analytically we can write it u of xy equals arctangents y over x. So this angle. Okay, so let us find its first derivative. So I claim that this is a harmonic function. Du dx equals 1 over 1 plus y over x square times derivative of this with respect to x. It is minus y over x square equals, now we can move x square here. It is minus y x square plus y square. Now du dy equals 1 divided by 1 plus y over x square times 1 over x. Now let's multiply numerator denominator by x, and then we get that it is equal x square plus y square. Now once again d2u dx square, we have to differentiate this. It is x square plus y square square, numerator times derivative of denominator, minus y times 2x. Yes? And derivative of y with respect to x is 0. d2u dy square equals x square plus y square square, and here it is x times 2y. Now if you add them together, we have d2u dx square plus d2u dy square equals 0. Yes? Identity. So this function is harmonic. Now, strictly speaking, we proved it only in the right half plane. So in the upper, lower, and the left, we have to use different expression for the polar angle. Instead of arctangents can be arccotangents and so on. But the result will be the same. And yes, of course it is the same, because we can simply turn all this picture by, say, 90 degrees, and by the same way prove it, even not prove, because after this turn we see that this angle, say here, is, if you turn it, it is the same as this angle, plus pi over 2, which does not change harmonicity of the function. And then we don't need to make this simple calculation once again, because we have this previous theorem that if function is harmonic in one position, then we can turn it remains harmonic function. So this is the first application of that theorem. Let us make a little break and then continue to the next important example. Okay, let's continue examples of harmonic function, and now it is example radial harmonic functions. So it is a harmonic function in n-dimensional space u of x, which depends on only module x. U of module x equals u of r. Let's denote r equals x1 plus square plus xn square to the power 1/2. So x in Rn. So these are functions which depend only on the distance from the origin. So the surface of level surface is a sphere, or no, are a sphere. Or if n equal 2, level surface is a circle for any radius. And so we are, if it is radial function, then it has the following form: u of x equals, say, v of r. Let me write it with different, because u is a function of n variable and v is a function of one variable. Let me correct. Equals v of x1 square plus xn square to the power 1/2. Now I want to find v of r such that Laplacian of the function u were 0. Now it is a matter of some computations which we are doing now. So first of all, I have to find some d2u dxi square, I from 1 to n. Now here is Laplacian u. Here it is symmetric for all the u play the same role, equal role. So I find it for one I, and then I use it for all I, and it will a little bit simplify situation. So let me find one of this second derivative. So du dxi equals dv of r dxi equals v prime of r times dr dxi. So we have to find dr dxi. Dr dxi equals d dxi of x1 square plus xn square to the power 1/2 equals 1/2 and all this is called r. So we have r minus 1, yes, times 2xi equals xi divided by r. R is where is r? R is here. So and so this means that du dxi equals v prime of r times xi divided by r. Now let us differentiate it once again. d2u dxi square equals, so we differentiate first this, v double prime of r times xi divided by r. It is derivative of this, partial derivative of this. Instead of v, I differentiate v prime, but times xi divided by r plus v prime of r times r square r times a derivative of xi by xi is 1 minus xi times a derivative of r dr dxi. dr dxi, it is xi divided by r, which is equal all this to the following: v double prime of r times xi square divided by r square plus v prime of r times 1 over r minus xi square divided by r cube. And now, so we found one derivative. For all I, they will be the same. The only thing is xi different. So delta u equals v double prime of r times sum xi square divided by r square, I from 1 to n, plus v prime, let me write it in the other line, plus v prime of r times sum 1 over r minus x let me write minus sum xi square divided by r cube, I from 1 to n I from 1 to n. Now, some xi square is exactly r square. Yes? R square, r is this square root of this sum. So r square is what is in the brackets. X1 square plus O plus xn square. So it is equal to v double prime of r. And here, sum of 1 over r from I from 1 to n, it is n divided by r. Sum xi square, it is r square. So it is sum r square divided by r cube remains r, 1 over r. So minus 1 over r times v prime of r. Yes, this. Okay, so we have the following equation, the formula. Delta u equals v double, I'm sorry, delta u equals v double prime of r plus n minus 1 divided by r v prime r. So it is true for any radial function which depends only on radius, and if you want this function to be harmonic, you should demand that this is 0. So if delta u equals 0, then v of r satisfies the equation v double prime of r plus n minus 1 divided by r v prime of r equals 0. So it is just linear second order equation. Now we see one obvious solution. It is constant, because here we have only derivatives, so every constant is a solution. V equals constant. And second, let us look for a solution in the form v of r equals r to some power alpha. And let us substitute just a minute. This equation does not contain v itself, so let's introduce the new variable w of r equals v prime of r, and then you have equation w prime plus n minus 1 divided by r w equals 0. W, let us look in the form r to the power alpha. So alpha r alpha minus 1 plus n minus 1 r alpha minus 1 equals 0. Alpha plus n minus 1 r alpha minus 1 equals 0. Alpha plus n minus 1 equals 0. And so we have alpha equals 1 minus n. And so w equals r to the power 1 minus n. And w is derivative, so v of r is integral r 1 minus n dr. And now we have two cases. The first case, n equal 2. In this case, v of r equals integral r 1 minus 2 minus 1 dr equal logarithm r. No, plus c, plus c. Second, n more or equal than 3. In this case, v of r equals r to the power 2 minus n plus c. Now say if n equal 3, it is r to the power minus 1. And so general solution v of r equals a logarithm r plus b if n equal 2, and a r to the power 2 minus n plus b if n more or equal 3. So this way we found the radial harmonic function. So it is not, we see such non-trivial functions, and we will use them and see why they are good and so on, starting from the next lecture. So for now, I think you are overfed with these calculations, so have a good time. Bye.